In the previous session, we have learned what is uniform quantization. We have learned two types of uniform quantization. Can you tell me what are those two types? Two types of uniform quantization. In the last class, we have discussed what are the two different types of uniform quantization. How many of you remember it? Mid-rise and mid-trend. What is the difference between mid-rise and mid-trend? What is the difference between mid-rise and mid-trend? Yes? So in today's class, we'll be dealing with non-uniform quantization. First of all, what is the need for non-uniform quantization? So today, we'll see why do we need to have a non-uniform quantization? What is meant by non-uniform quantization and how we are going to compress and what is the need for all these things? We came to know that uniform quantization we have a standard step size. That means you have a standard value with which each quantization levels are being upgraded. In non-uniform quantization, you can note that we have different step sizes. You have a small one here, you have a big one here. You can have it in either way. It's not necessary that we can learn why we are doing all these things because we have some advantages. That's why we are working on all these kinds of different levels or different types of quantizations. But in practice, what we'll be doing is that we're having a communication engineering lab in the next semester where you will be learning how to quantize a signal. You will have to do all these things in practice. Analog and digital communication, you have theory here. The next semester you have a communication engineering lab. And if you need to clear those papers, you need to know a thorough understanding of all these things. So in the lab, it is not easy to pass because you have to do it all these things in practice. You don't have non-uniform quantization in practicals, but you will be having uniform quantization and you have to do uniform quantization. So what is uniform quantization, non-uniform quantization and why do we need non-uniform quantization? There is a good signal to noise ratio for large amplitude signals, but what happens when the amplitude is very low? When we consider speech signals, we have the voice signals that is being generated with low amplitude. In most cases, we'll be having low amplitude and we don't have any kind of uniform way in which we have speech signals generated. We have, when I'm speaking all of a sudden louder, we have a shorter duration and a higher amplitude. Are you able to understand what I'm saying? So, the speech signals or the message signals which we intend to transmit are not uniform. They are always varying. You have short pulses, you have high amplitude short pulses, you have low amplitude long pulses and so on. So this slide explains about the ratio of intensities when we speak or when we generate voice signals. Certain signals are to be assumed in that manner. So what happens in these cases? This is what brings us to a need where we need to start thinking about non-uniform quantization. Last class I've discussed with you what is quantization in detail. You know that we have an amplitude signal, an analog signal that is varying according to the message signal. Now we have to quantize the signal. Quantize the signal means you are assuming a set of digital values to each and every point in that analog signal. Is that clear? Have you understood what I've told? Now this particular slide explains why do we need to have a non-uniform quantization and why do we want to adopt to a different strategy other than the mid-rise or the mid-rate quantization methods. Okay, and keep in mind this is the first introduction to a question that is being asked very commonly in your exams. What is the need for non-uniform quantization? Then introduction. We have voice signals that have short duration but high amplitude. So non-uniform quantization is the best solution for quantizing different kinds of signals which is having a very low amplitude. You can imagine that when the amplitude is lower, you might see that. So when you send a voice message in WhatsApp, you can see how the amplitude of the signal varies. WhatsApp voice messages, have you noticed that in most of the times the voice message will contain there is a very low amplitude signals. Only when you speak, all of a sudden you will have a high amplitude. So this is one example with which you can understand more about non-uniform quantization. That means that in most cases what we'll have is that our voice is low amplitude, and Q is small even though we have a fixed number of quantization levels. In non-uniform quantization, the step size changes. So for speech signals, the signal amplitude is low most of the time, and all of a sudden you'll have high peaks. So it is always better to have the signals where we have high peaks or higher amplitude. We need to have a different quantization mechanism. That's why we adopt to non-uniform quantization. We get a good signal to noise ratio. So for a question on why we need non-uniform quantization, you need to give these explanations. Okay, and one of the most important reasons why we need to adopt for non-uniform quantization is that we have a high signal to noise ratio when we have a varying set of step sizes. Is that clear for all of you? So here it is that wherein the prescribed quantization levels are not uniformly spaced. Assuming that the quantization is memoryless, the use of non-uniform quantizer is equivalent to passing the signal, the message signal through a compressor and then applying the compressed signal to a uniform quantizer. So the things that is not visible here is and then. Voice signals are more likely to have amplitude values nearing zero. We have very small values for voice signals. the amplitude is not very high. So digitizing that low voltage signals, and we have to amplify that. That's why always whenever you transmit or whenever there is a difference in sound, right? When you digitize or when you convert your signals into voice signals into electronic signals, you naturally have a higher amplitude and a higher pitch. Am I right? The voice signals are not the same signals as you are speaking. There is a change always. Am I right? So one of the reasons for that is that the amplitudes are usually very low. So it is always better to have a non-uniform amplitude distribution, and we have a granular quantizing noise. That means that the quantizing noise, when you convert these voice signals, low amplitude signals, already the amplitude is low. You're breaking it into further pieces, you will have more grains developing in your quantized signal that increases your quantization noise. So this can be avoided by using non-uniform quantization. The questions that appear for your exams may be of different types. It could be like this: why do we need to have a non-quantization method? Second, what are the advantages of non-uniform quantization when compared to uniform quantization? Okay, so what are the points you can write? First thing is that you have a higher signal to noise ratio. You don't have grains. You don't have any kind of disturbances in the voice signals in case you are preferring to go with non-uniform quantization methods. Okay. So next, how do we use or how do we create a non-uniform quantized signal? The basic block diagram is like this: that you have a compander. Compander means compression and expanding. You have a compressor here, you do the uniform quantization, you reconstruct it and then expand it by using the inverse of the compressor. The basic block diagram of creating a non-uniform quantized signal. We call it as companding. Companding means compression plus expansion. What we do with the initial signal, we compress it, then we do uniform quantization. We reconstruct the original filter using a reconstruction filter. We reconstruct the signal, and then what we do is that we expand the compressed ones. And these kind of companding techniques are widely used even today in so many applications. You need to study and understand very clearly what is meant by companding. So let us see what is happening in the compressor side of a non-uniform quantization. We'll be studying two laws. First one is called as mu law and the second one is called as A law. For mu law companding, how the signal is getting compressed. Study the first compression technique, which is called as mu law, wherein the amplitude is defined as the natural log of 1 plus mu of m by natural log of 1 plus mu. This is called as mu log companding, wherein natural log is log to the base e. M and V are the input and output voltages of the compressor, and mu is a positive constant. In mu log companding, the output of the compressed voltage will be the natural log of 1 plus mu into absolute value of m by natural log of 1 plus mu. Mu is a constant, m and v are the input and output voltages of the compressor. So when we make a signal wherein the output voltage V is of this form, we call it as mu law companding or mu law compression. The same principle is applied while expanding also. So what is mu law companding? Compression. The output, the V voltage is equal to the natural log of 1 plus mu absolute M by natural log of 1 plus mu, and mu is a positive constant. Okay. So when you are given problems, you will be given the value of mu. So listen here. The case when the value of mu is equal to 0 is equivalent to uniform quantization. When mu is equal to 0, it is uniform quantization. For any given value, we are finding out the slope of the compression curve, which is dm by dv. We don't take the negative values, we take it as absolute values. In that case, we'll get, what we'll get? Natural log of 1 plus mu by mu into 1 plus mu into absolute value of m. M is the input voltage, right? And mu is a constant that we are going to define. I hope you are clear with this. You want any further explanation? So the next type of compression and expansion technique is called as A law. Similar to mu law, the definition of A law is given here in this slide. The absolute value of V is equal to A into absolute M by 1 plus natural log of A, where M falls between 0 and 1 by A. And when it is above 1 by A to 1, we have 1 plus natural log of A absolute M by 1 plus ln A, natural log of A. And similar to mu law, A is a positive constant. So this is the formula with which we are going to compress the input signal, especially in cases of voice signals where the amplitude levels are comparatively very low. So we have studied two types, A law companding and mu law companding. When A is equal to 1, it corresponds to uniform quantization. In mu law companding, when mu is equal to 0, it corresponds to uniform quantization. And in this case, in A law, when A is 1, it is uniform quantization. So I told you that A is a positive constant and the general value for A is 87.6. If you get problems where you are not given the value of A, you are supposed to use this value A to be 87.6. You have to keep this value in your mind, and in case you are getting problems where you are not given the value of A, you need to use 87.6. Now, like what we have done for the other one, like mu law companding, we are finding out the reciprocal scope of this compression curve by finding out the derivative of m with respect to v. So this is how we represent graphically the normalized input versus normalized output in case of mu law and A law companding. Write down this question. Solution to this question we'll see in the next class, next session.